Good morning, everybody. So we'll get started back in chapter 9. So chapter 9 is getting into, of course, three-dimensional shapes of molecules and how we can predict those shapes from a Lewis structure, and starting to take note of how many, we might call them domains or sort of things there are in a central atom. So if you look at CO2, we have two domains. You might look at a double bond and say, is that two domains because it's one double bond? The answer is one double bond is one domain. The other double bond is a second domain. And the issue is those two domains just want to get as far away from each other as possible, because those lines represent electrons. Electrons repel each other. So those electrons would much rather be 180 degrees relative to each other, of course, than say 90 degrees. Like, we wouldn't want to have this. That would be a bad orientation for CO2, because those electron pairs in the bonds would be too close together, would repel, and the repulsions would kick it into being 180. And so then if you look at something else like HCN, the triple bond here is still just one domain. The single bond is just one domain. So again, we have two total domains. I want to make sure that we're not counting a triple bond as itself being three domains. A triple bond is just one single domain, because that triple bond wants to get away from the single bond. So again, HCN isn't going to look like this. This would be a very bad geometry, right? It seems like if we wanted HCN to exist with this type of bond, that there's going to be too many repulsions between the single and double bond, and so it's not going to adopt that geometry. And so then if we have three total domains, we can have three domains two different ways. We can either have three bonding domains, where all the domains are some sort of bond. Could be single, could be maybe one of them's a double, like in formaldehyde. So these here have three domains. Those three domains would want to get 120 degrees away from each other, and that's the way that they can best get away from each other and have the least amount of repulsions. If you try to pull the electron pairs like out of the plane and have the central atom in the plane, that's going to reduce that bond angle to be less than 120. Being less than 120 would mean more repulsions. So 120 is kind of the greatest bond angle we can have with three things, so they can all get equally as far away from each other. And so 120, we also could get 120 degree bond angles for something like NO2. This would actually be NO2 minus. But for NO2 minus, where we have a lone pair on nitrogen, that's going to kick that structure also into being this trigonal planar geometry for having three total domains. So we have a double bond, a single. We have resonance, but that almost doesn't even need to be considered. The resonance would just mean we still have three total domains around that nitrogen atom. And so if you're picturing this nitrogen as the composite structure, we would have something like this, and that would still be within that trigonal planar domain, because we'd still be counting one domain, two domain, and then three domains. So three domains would go trigonal planar. Then having four domains kicks it into finally like using three dimensions, or needing to use three dimensions is trigonal, is tetrahedral once we have four domains on a central atom. So at this point here, we might have to start drawing wedges and arrows to try to portray the third dimension. Linear, trigonal planar didn't really need us to draw structures with wedges and arrows, but if we're drawing something like CH4, we'd have our carbon, hydrogen, and just picture one coming out at you and one going back into the page. Relatively easy to draw the structure. If you start to rotate the structure, there might be other ways you could sketch this structure, but if you get in the habit, I think, of just taking like let's say water, so we know water in terms of a Lewis structure, we might write the Lewis structure without much thought of the geometry of the molecule, but when we're thinking of the actual molecular shape of water, we're going to picture oxygen having four things attached to it in this tetrahedron shape. And then just imagine, let's use the wedge and arrows for the hydrogens, and then let's replace these positions here with our electrons. And let's imagine those electrons are in some kind of orbital that are in that sort of direction of the tetrahedron, so that the electron bond angles are about 109.5 degrees, the hydrogen bond angle 109.5 degrees. Now, whenever we start to have electron pairs versus bond pairs, we can start to think a little bit about the geometry probably not being perfectly tetrahedron. You know, that perfect tetrahedral would be 109.5. That's what we would get for methane. So these bond angles in methane would be exactly 109.5. Because that's perfect tetrahedral, and there's no way one of those bonds repels the others by more, because the bonds are exactly the same. But in water, we have a little bit of a different case. Those electron pairs, you can imagine a lone pair electron is going to be closer to the oxygen atom. The bond pair electron is going to sort of stretch out the electron pair. It's going to be like further away from the nucleus. So you're probably going to get a greater repulsion, you would imagine, between the non-bonding electrons and the bonding pairs. You're going to get a greater repulsion because they're closer to the nuclei. So we're going to get a bond angle for the HOH bond angle that's a little less than 109.5. And we're going to get, if you could measure the electron bond angle, if you could measure this bond angle, it'd be a little bit greater than 109.5. And that's just because you get greater lone pair repulsions because they're closer to the nucleus of the oxygen atom. So they repel each other more. They'll push the oxygens to be a little closer together than perfect tetrahedral. There's a slide that shows this later, so we'll come back to this topic in a minute. Yeah?
So it's not considered planar? It's not in bonding?
So, well, you can write it planar, but the electron pairs wouldn't be planar. So in terms of writing water, the key would be that it's not 180. If you look at this structure here, and you think it's 180, that it's not 180. It's closer to 109. It's actually a little less than 109. And then whether or not you draw wedges and arrows, like if we want to draw water like this is like perfectly fine to draw water like this, but then these electron pairs, we're going to be picturing them coming out and then going back. And so it's just a matter of how we're going to like picture, like if the water's here, then the electron pairs are like here. And so then if we picture electron pairs here, then the H and O are sticking out and into the page. So it's just some way of seeing that three-dimensional shape for a molecule that has a bond geometry that ends up being like the actual geometry of the bonds of the H and the O and the H are planar relative to each other, so you can sketch it planar. And a lot of times we would still sketch water, like we might write a Lewis structure like this, and that's fine, but we're just picturing those electron pairs aren't really in the plane of the paper then. So keep this in mind. Whenever you see a Lewis structure, that we may not be giving you the true three-dimensional shape. Let me give you an example real quick. So let's look at methanol. If we write this as our structure for methanol, you'll see a Lewis structure. We've written this Lewis structure this way before, and we might ask you, well, what would you approximate as the HCH bond angle? Like, what is this bond angle here? You may say 90 degrees because it looks 90 degrees in the structure. The real structure, though, would be tetrahedral because you'd be looking and saying I have 1, 2, 3, 4 domains. So this carbon here is tetrahedral. Tetrahedral is close to 109.5 degree bond angles. So we'd expect this bond angle to be 109.5 degrees. So we don't always sketch, and often we don't sketch three-dimensional shapes with Lewis structures just because it's complicated. It's harder to sketch those out. It's harder to typeset those if you're making notes or whatever. So the real structure of methanol is going to look something like so it's going to look something more like a structure that has some three-dimensional shape to it. So we can interpret that three-dimensional shape. We can see that this bond angle here should be closer to 109.5 degrees. We could pick up the lone pairs, probably reducing that bond angle to be a little less than 109.5. So we can start predicting whether the bond angle should be really close to 109.5 degrees, in some cases like CH4 exactly 109.5 degrees, or whether it should be a little less if we have some lone pair repulsions. Let's just push through. You'll see, like, we got plenty of examples that are probably going to get the questions that you're going to ask. And so ammonia. So how do we do this for a random molecule? So we give you a molecule. How do you determine its molecular shape, its molecular geometry? Well, the best thing we can do is start with the Lewis structure. So if we're starting with like NH3, the issue would be, well, let's write nitrogen, single bond the atoms of the central atom, complete their octets, hydrogen's complete as is, and we would count up our 5 plus 3 for 8 electrons. The 2 leftover electrons go on to nitrogen. And so we end up with the structure for nitrogen that has a lone pair, 3 bonding domains. So when I see this Lewis structure here, I'm counting 1, 2, 3, 4 domains. So that nitrogen should have a tetrahedral, what we call electron domain. So meaning all those domains on nitrogen should fit the structure of being tetrahedral. So we have an electron pair here, have a hydrogen, then hydrogen coming out and then going back. So what we want to do is from the Lewis structure determine the sort of electron domain geometry based on the total bonding and non-bonding domains. So what that just means is we're counting like the bonds attached to a central atom, and then we're counting the number of lone pairs on that central atom. And so for this example here, that was 4, and 4 fits into those domains separating by being tetrahedral. And so then we use the arrangement of the bonded atoms to try to determine the molecular geometry. And probably the weirdest thing about this is you then try to say, well, what's the shape of just the atoms? Like, what's the geometry name you might call just the atoms? And you almost ignore the electrons for the name of the shape, but the electrons are still very important because they're determining the shape. So the fact that there's electrons here kick it in the tetrahedral, but then we try to say, well, what name might you just give the actual atoms? And the reason why you do this is if you try to determine the structure by some like X-ray diffraction, you can see the nuclei by X-ray diffraction, but not the electrons. So you can determine a geometry experimentally by sort of seeing where the nuclei are. And so you give a geometry name for just like the atoms or the bond geometry. Often we just call it the molecular geometry. And so if you can look at this shape here, you try to say, well, what's the shape of the atoms? And if you notice, you get this trigonal, and then it's a pyramid. See how it's like a trigonal pyramid shape? So you're really just trying to say, well, what's the shape that emerges from just the bonds or the atoms in the structure? And so that's going to be trigonal pyramidal. So we get a pyramid shape of a trigonal. So we would call this trigonal pyramidal. I don't know why I wrote that, it's right here. Okay, and so basically whenever we have a geometry that we don't know, or a structure we don't know the geometry of, we just think domains, think how those domains want to separate, and then try to think of how we would name the shapes that emerge from those structures. And so let's go through the three possibilities for tetrahedral. So tetrahedral can have three different geometries. It could have where all the domains are bonding. That would be tetrahedral molecular geometry. So that's something like CH4. So CH4 would be tetrahedral domain geometry, and then tetrahedral molecular geometry. And so these are all tetrahedral domain. And then we have tetrahedral molecular geometry. Then in the case of ammonia, we saw that we have an electron pair here that kicks that into being the fourth domain for tetrahedral, but only 3 bonding domains, so we call that trigonal pyramidal. And so this would be something like NH3 having that lone pair on nitrogen. And then water would be something we would call bent. So water with 2 lone pairs on oxygen. So lone pairs are taking 2 of the spots in the tetrahedral structure, in the tetrahedral electron domain. And then we're trying to say, well, what would you call this geometry here? And it's really for 3 atoms where you just have 1 bond, or excuse me, where you just have 2 bonds. It's just a question of, is it completely linear, or is that bond bent? So if it's perfectly 180, we'd call it linear, like CO2 is linear. This one here, we would call this structure bent. So we'll see a few different bent structures. In fact, if you go back to the molecular geometry for NO2-, so for this structure here, we didn't give a name to this on the page when we were talking about this a couple slides back, but we would call this structure bent as well, because this geometry here is not 180, but it's closer to 120 degrees. And then you can even go back to an approximation. Do you expect it to be exactly 120? Probably not, because we have this lone pair repulsion. It's probably going to kick the nuclei of the oxygens closer together, so probably a little less than 120. Let's look at some larger geometries, and let's come back to some lone pair bond pair repulsions. We'll look at some actual bond angles of a few molecules to see just how much those lone pairs can perturb a structure. So you can have more than 4 domains, so having 5 domains would kick into an electron domain geometry of trigonal bipyramidal. The name may sound strange at first, but you have the trigonal structure on the equator of the atom, and then you have the pyramid shape that emerges on top, then you get a pyramid structure on the bottom. So you get a bipyramid structure. We get this with something like PF5. If you look at the Lewis structure of PF5, we would have 5 plus 5 times 7, so there's 40 valence electrons, and this would have a structure of phosphorus with the 5 fluorines attached. When I do the Lewis structure, I don't really think too much about shape. We're just trying to really see how many bonds are there in the central atom, are there lone pairs. If I do 5 electrons per fluorine, there's no electrons left over for phosphorus. So we have 5 bonding domains, 0 non-bonding, so we're fitting into this category of having 5 total electron domains. So 5 domains, the best way that these domains can separate the structure the molecule adopts is where you imagine having your phosphorus. I would kind of picture having this here, a fluorine coming out at us, going back, where these are perfectly planar relative to each other. So this would kind of look like BF3, but just like rotated on our page so that our fluorine's coming out and out at us, coming out and back into the page. And then just imagine having an axis with 2 fluorines on it, above and below, that kind of cap off having that bipyramid structure. So hopefully you can see the kind of bipyramid we're getting from this like trigonal structure on the equator of the molecule. And so our bond angles here kind of go 2 different ways. You have 90-degree bond angles here, and then you have 120 on the equator. So you have 2 different sets of bond angles, depending if you're comparing the fluorines that are on this sort of the equator of the molecule, 120, and then the axial to the equator bond angles are 90 degrees. And then, of course, you have the fluorine to fluorine 180 degrees if you compare the 2 fluorines that are on the axis together. There's a couple different ways of thinking of the bond angles we get in trigonal bipyramidal. We'll look at having fewer, like you can go through the sort of process of having 4 bonding but 1 non-bonding domain. What structure does that take? We'll see a slide on that in a minute. So we'll look at a couple of other shapes within trigonal bipyramidal in a minute. But let's just first then, look at having 6 total domains. I mentioned before this is kind of a weird one where it was 6 domains, but octahedral, octa 8. But the 8 isn't coming from 6 things attached. We'll see what that comes from in a minute. So for octahedral, this is where we have 6 domains. This might be something like SF6. So you have 6 plus 42 for 48 total electrons. And so that's going to be 8 per fluorine. So that's just having sulfur, fluorine, fluorine, where we have 8 electrons each. Then we just do this again. And we can imagine one going back and coming out of the page. And this would be coming like straight out of the page. So like if we're drawing our SF4 so far, so if we're drawing these fluorines in the plane of the paper, then this fluorine's like literally sticking like straight out of the page. And the other one's going straight into your page. So it's a little bit hard to draw that 3rd dimension. There's a few different ways you can think of sketching it too. Like we could have sketched it maybe where we took the sulfur, keep these fluorines together, and then have a wedge arrow this way and a wedge arrow this way. But either way, hopefully you're seeing that you're getting 6 fluorines attached, and you can almost see a name that could have emerged. In fact, a name of square bipyramidal might have been better, because you can kind of see that this like trigonal bipyramidal has like a square that you get 2 pyramids from. So you're getting like a pyramid structure on top and bottom. But then the name octahedral comes from, if you think of having that square bipyramid, the pyramid on top has 4 wedges, and the pyramid on the bottom has 4 wedges. And so the shape that you get here, if you think of all these triangles, that you get a total of 4 on top and then 4 on the bottom. So that's what the 8's coming from, is you get like an 8-sided shape that emerges from these 6 atoms attached to sulfur, or whatever the central atom is. And so we get like an 8-sided shape. And this kind of goes back to tetrahedral being tetrahedral, not necessarily because it has 4 atoms attached to a central atom, but because the shape that emerges in the tetrahedral, so if you think of this shape here, the tetrahedron is really more about like the shape that you get on that structure. So like you get, if you connect all the atoms, you get a 4-sided pyramid. For octahedral, you get the 8-sided pyramid from all those atoms being connected on the periphery of the molecule. Okay, so 6 total domains, all bonding. We would say the molecular geometry and the electron domain geometry would be octahedral. And so the task for like the Lewis structure for an unknown molecule is sketch the Lewis structure, make sure we get the lone pair count right. Like that's really the most important part of a Lewis structure, I think, is seeing when you have leftover lone pairs. Because it's going to make a big difference if you have a central atom with 4 bonding domains, 0 non-bonding domains, and it's tetrahedral. If you have an atom that has 4 bonding domains but 2 electron pairs, it's going to fit into this octahedral domain. And we're going to have to think of the shape that we get for the molecule from being octahedral. Okay, so let's like kind of go back to like something like SO3 2-. Let's see if we can sketch a Lewis structure. A lot of times, like if you were arguing over, do you expand an octet with more double bonds to minimize formal charges, it almost doesn't matter. So if you get to the point, let me have you guys try to think of the Lewis structure of SO32-, try to count domains, try to see that it doesn't really matter if you're going to draw SO32- with 1 or 2 double bonds. It's really not going to make much of a difference, but just get to a point where you can count the bonding and non-bonding domains, get the total number, and think about then the structure we're going to get. So let me give you guys about 2 minutes to think about this question here. That was a fast silence. Nope. Okay, so let's take a look here. So for SO32-, one of the keys is just the count. You know, counting 6 for sulfur, 3 times 6 for the O's, plus 2 for that negative charge gives us 26 total electrons. If we miss this count, if we're not thinking of that count, we may not get these 2 electrons here on sulfur. That we're only getting those 2 electrons on sulfur by single bonding the oxygens, giving them an octet first, counting up only having used 24 electrons to get the 2 left over that go onto sulfur. So if you had missed those 2 electrons, you may have said, you know, it only has 3 domains. And you may have been quibbling over whether it's, you know, 1, 2, or 3 double bonds. But the problem is we actually have a lone pair of electrons here, so that's going to kick us right away into having 1, 2, 3, 4 domains. So we're going to be, you know, having 4 domains for this molecule, and then only 3 of them are bonding. And so we have 3 bonding domains, so the answer is going to be C. Now, it doesn't matter if the bonding domains are single or double bonds. So like we can argue as much as we want over whether or not this is the best Lewis structure, which I think it is, or if we should maybe factor in the plus charge on sulfur, the minus charges on all these O's, and make a double bond. So if we go to this structure here and say, well, let's say we think this is a better Lewis structure. And I think it's debatable, but it doesn't matter, right? Because this is still just one domain. So this is one domain, this is our second domain, 3 and 4. So we still have 4 total domains. So it doesn't matter if it's a single or double bond. So for a Lewis structure, in like chapter 8, if we want you to tell us how many like single bonds there are in SO32-, we have to say with what rule we want you to apply. We would have to say with, you know, the application of the octet rule, or by minimizing formal charges, what's the proper Lewis structure. In chapter 9, it doesn't matter in terms of the shape. So a lot of times we're not going to tell you for the Lewis structure what to factor in terms of the Lewis structure, because it's not really going to play a role in the Lewis structure. So 4 total domains, 3 non-bonding. So then the shape of this molecule should be tetrahedral domain. That just means all those electron domains fit into tetrahedral, and then one of them's non-bonding, so that fits into that trigonal pyramidal. So we can start to think of the shape this molecule would look by factoring in what tetrahedral looks like and just replacing one of the spots with the lone pair, the others with the oxygen atoms. Okay, so let's compare, water, ammonia, and CH4 here. And so the issue with a bond is that we're stretching out those two electrons so that their repulsions are going to be lower, and then what we have is the electrons being closer to the nuclei and kind of being in a larger size orbital. So the electrons on our nuclei, these are negative particles, so these are going to be closer to the nucleus in like a larger orbital that are going to have greater repulsions with those bonds that are attached to a central atom. So this is how we can look at CH4. Again, the bond angles have to be perfectly 109.5 because all those domains are exactly the same as each other. And then ammonia, with the lone pair repulsions kicking those bond pairs a little bit closer together due to having greater lone pair bond pair repulsion. So the lone pairs are repelling the bond pairs more than the bond pairs repel each other. And so that kicks us into being a little less than 109.5 by like 2 or so degrees, by 2.5 degrees. And then water is about 104.5. So having a second lone pair, they put the lone pair going back and sticking straight up. And so this is pushing the hydrogens a little closer together, again, due to having greater repulsions of those lone pairs with the bond pairs than the bond pairs with each other. So the bond pairs are just taking the electron pairs, stretching them out so they can get a little closer together. And so you can see here that we're close to 109.5 degrees. So if we said, is water tetrahedral in shape? It is for its electron domain geometry. Is it perfect tetrahedral? No. Is it close to it? Yes. It's a couple of degrees off, and we can sort of predict the direction that those angles are off. And so then we can also see this come up with double bonded structures. So having a double bond, we now have 4 electrons here, only 2 electrons in the single bonds. And so having 4 electrons going to have a greater repulsion on those single bonds. So the extra electrons are going to push the single bonds a little closer together. And then, so the angle is not perfectly 120 for something trigonal planar like CO, Cl2, but closer to about 124 for the double bond, single bond angles, and the single bond angles a little less than 120. And so I would say here we would just want to be able to predict this should be less than 120, and this angle here should be greater than 120 by a couple degrees. It still doesn't flip out a plane, the structure is still perfectly planar, so this is still a trigonal planar geometry, just not perfectly trigonal planar. So we just get greater exertion between double bonds with the single bonds than the single bonds have with each other. And it's just due to having greater electrons making up that double bond. Now we have to be a little careful to not outthink ourselves. If we go to a structure for SO3, so SO3 without the 2- charge, so this is just SO3 with a neutral charge. This structure here has 24 electrons. This structure here doesn't benefit from having those 2 extra electrons in the central atom like the SO3 2- example previously. So this structure here, if we want to satisfy the octet rule, we might sketch a Lewis structure that looks like this. If we actually wanted to sketch a Lewis structure that minimized formal charges, we'd be writing a structure that looked like this. We'd have this structure here with 0 formal charges all the way around the molecule. And maybe this is actually a better Lewis structure, because in this structure here, I don't think we're going to argue that all those bonds are exactly the same as each other, so they repel each other exactly the same. So all these bond angles are perfectly 120 degrees. Well, in this Lewis structure here, we have the resonance of this electron pair over to here, and we have the resonance of that electron pair over to here as well. So that double bond will resonate with the other 2 bonds, and we never really have the double and 2 singles. We really have that 4/3 bond. So all these bonds here are really the same. They're really 4/3 bonds within this Lewis structure. So even if we picture the Lewis structure on this side here, all those bonds are exactly the same as each other. We just have to think about resonance. So all these bond angles here are still perfectly 120 degrees. So these would all be exactly 120 in both of these Lewis structures here. So we just have to picture resonance. A little bit trickier, but we have to not out-trick ourselves into thinking, well, the double bond's going to push the single bonds closer together. Well, we really don't have a double bond. So we just have to make sure to take into account resonance. We only have resonance when the Lewis structures are exactly the same. So the reason why I bring this up is I want us to imagine we're not getting resonance in the COCl2 structure. You would have to have, for resonance, the exact same Lewis structure. Like when we think of one of these other Lewis structures, we get the O, the S, O minus, O minus. We get the exact same Lewis structure, just making up a different SO double bond. So resonance is where we can have equivalent yet different Lewis structures, averaging out. They average out to 4/3 bonds, where those bonds are exactly the same. So for resonance, it doesn't really lead to the changing of the bond angles because the bonds are all exactly the same. Okay, so let's think a little bit about electronegativity differences. So from chapter 8, we would look at a bond and just say if you pick a particular set of atoms, you can determine if their atoms differ in electronegativity. If they do, the bond would be called polar. The greater the difference of electronegativity, the greater the polarity of the bond. But what about molecular polarity? We were talking about this with regard to CO2, where these bonds were sort of exactly opposing each other and canceling out their dipole moments, or we were having one end of the molecule was the same charge as the opposite end. The dipole moment of CO2 turns out to be exactly equal to 0. That's a characteristic of a nonpolar molecule. So nonpolar molecule, despite having polar bonds, so the bonds are polar, meaning that the atoms are polarized into plus and minus charges, but not in such a way that one side of the molecule has a greater charge than the other. So if I have two adjacent CO2s, the question is, do I get built-in attraction or built-in repulsion? I get repulsion, not attraction between these molecules. So if I think of just like aligning CO2s, I don't get attraction, I get repulsion. That's going to weaken their force of attraction. That's going to reduce their boiling points and melting points from what they could have been if the molecule was polar. If you compare this and contrast this, we contrasted this with water, where having that bent bond of water gave it this dipole moment here, this negative charge here. So here, if we stack our water molecules, we get this built-in plus minus attraction. So we get a built-in attractive force between water molecules because of these molecules being polar. So we get some dipole moment of water. It's close to 2 dBi in that unit. But if you know a molecule has a dipole moment that's greater than 0, then the molecule is polar. And the molecule is polar for 2 reasons. One, because it has polar bonds, but then 2, that the bonds are situated in such a way that one side of the molecule picks up a net different charge than the opposite side of the molecule. So we have a net positive side of our molecule here, and a net negative side of our molecule on the opposite side of water. Now for CO2, you might say, well, what about the plus in the middle, the minuses on the outside? The minuses are canceling out that positive charge in the middle. So we have to have like an imbalance in charge. We have to have a bent bond with a positive charge here, negative charge coming downward, or something that allows one side of the molecule to have a different charge than the other side. Okay, so bond polarity is a measure of how equally or unequally the electrons are attracted to the different nuclei in a bond. So a nonpolar covalent bond is just one where the electronegativities of the atoms are very similar, or maybe exactly the same. So if you look at the F2 bond, for example, this is a classic example of a nonpolar covalent bond because the nuclei is the same. Despite being really electronegative, the electronegativities are the same. They cancel each other out, so we get 0 charges on both sides of this molecule. So F2 would be nonpolar. For diatomic molecules, it really just comes down to differences of electronegativity. If the bond's polar, the molecule's polar. But whenever we have a molecule that has more than 3 atoms, the molecule's polar when it contains polar bonds, and the bonds are situated in such a way that the molecule's polarized, in such a way that one side's a different charge than the opposite side. So molecules are polarized when their ends differ in charge. And for diatomic molecules, this is really simple because their ends, if they're different electronegativity, will always be different in charge, of a plus side and a minus side. So then you get this dipole moment. If you think of CO2, if you almost think of just the sort of math problem of having 2 dipoles opposing each other where the dipoles are exactly the same, then they just simply annihilate each other and cancel each other out into giving the real molecule an exactly 0 dipole moment. And we'll go through almost every structure we've seen so far, but if you can imagine having all the domains are bonding, no non-bonding domains, will always be nonpolar if you have the exact same atom in every spot. So BF3 is really polar, right? Because that's definitely a polar bond. These fluorines are really negatively charged. Boron partially positively charged. But notice you get the same negative charge on every end of the molecule. So every side of the molecule has the same charge. So whenever you have a geometry where you have no non-bonding pairs of electrons in the central atom, and then all the domains therefore are bonding, And then if all the bonds are exactly the same, then the molecule has to be nonpolar. So BF3 would be nonpolar. If we go back through another quick example of, well, what about something like COCl2? We just saw this on the previous page. This is also trigonal planar. This molecule is also negatively charged on each one of its atoms. But the difference between COCl2 and BF3 is that the negative charges aren't exactly the same as each other. So the negative charges are different from each other. That these negative charges here, just because the carbon-chlorine bond has a different electronegativity difference, is different than this negative charge. So by having different atoms, even though they're all still negatively charged, but they're different in charge. They're different in the degree of that negative charge. COCl2 would be a polar molecule. So only when we have something that's, say, trigonal planar or whatever geometry with the exact same atom in every spot would the molecule be polar, would the molecule be nonpolar despite having polar bonds. So usually you look at a molecule and say, well, you know, if you have fluorines or oxygens, nitrogens, things that are relatively electronegative, if they're bonded to things like carbon or hydrogen, which are not very electronegative, those bonds are going to be polar. But then we have to have the molecule situated in such a way that the molecule picks up a net sort of polarity difference from one end to the other. And we'll see a bunch of examples. So like we're going to go through and look at a bunch of examples as we go. This is just comparing what we saw. I think we were looking at this Monday for CO2 versus water. And so we get this same negative charge here for both ends of CO2. We get these dipoles being exactly the same, canceling each other out. You get a tug of war where neither atom's winning the fight. And so CO2 would be nonpolar as a result. So overall dipole moment exactly 0. If we could just perturb this anyway, like if you go to COS, so you have oxygen, carbon, sulfur, just replace an oxygen with a sulfur atom. Sulfur is relatively electronegative. We still pick up a negative charge, but just a smaller partial negative because it's not as electronegative as oxygen. We're going to get a bigger negative charge for oxygen because it's more electronegative than carbon and get a bigger difference of electronegativity. So the ends of this molecule now have both negative charges still, but different negative charges. We then will have a net dipole moment for the molecule pointing towards the oxygen. So you have like a net pull towards oxygen. You put two OCSs next to each other. You get more of a built-in attraction than you would if you had CO2. So we'll see in the chapter on liquids in chapter 11 that having polarity allows molecules to be more strongly attracted together. So polar molecules exhibit a greater attraction with themselves than nonpolar molecules do. So we see water, partial positives here for the hydrogens, partial negative, definitely has a dipole moment. The dipole moment of water stems from the geometry of water being bent. So if water were linear, then it, like CO2, would have been nonpolar. So water being bent was really important for it to be a polar molecule. It's really important for water to be polar for it to have the properties it has of having a relatively high melting point and boiling point. Okay, so this, just going through a couple examples, like we actually had seen HCN already, but one of the things is like, how do you come up with a Lewis structure is some of these problems where we give you a structure, how do you get the proper Lewis structure? Well, these atoms here are just H to C to N, so we have carbon as our central atom. And then the way we'd come up with the Lewis structure is just to do maybe our rules of this way here, and then think we have a 2+ charge here. How many electrons have we used versus available? We had 10 electrons available, 2, 4, 6, 8, 10, 10 used. So no lone pairs for carbon. We have a net positive charge. We have room for electrons, so we can reduce that to plus, and we can reduce that to 0 by making a triple bond. So we make a triple bond and have nitrogen with that one lone pair. And so then if we're thinking of the geometry name, usually we're thinking for the central atom. Like what's the geometry about the central atom? Perfectly linear, right? So this is going to be linear, perfectly 180. And even though we have a triple bond, there's nothing else for it to repel. It's only one single bond. So if it repels the single bond more, it kicks it this way, then there's still a triple bond and repels it back. So it has to be perfectly 180. There's really no way this molecule can have anything but a perfect 180-degree bond angle. Because you have like one domain, if it repels it one way, then it's like, you just push me closer to that triple bond on the other side of you. Do you see what I mean? So like the triple bond, it has to be perfectly 180 still. And so perfectly 180, and then this would be linear. ozone, this is all about the Lewis structure, right? Like it's all about getting that lone pair on the central atom here. So like when we look at ozone, 3 times 6, 18 electrons, all three of the oxygens have to be connected. I don't know how else we could have 3 atoms. I guess we could have like some weird ring structure, but that seems peculiar. But we're just going to connect all 3 atoms together. Follow the rules. The non-centrals get an octet. We don't yet fill the octet on the central atom until we count electrons. So we count our electrons used, 2 left over, go on to the central atom. The central atom only has 6 electrons, could have 8. The central atom has a positive charge of +2. So the central atom here, if we're calculating the formal charge, is 6 minus 4 for +2. And so then we can kick in a double bond, and that reduces the formal charge to 6 minus 5 for +1. We can't kick in another double bond. Despite still having a positive charge, we can't make a second double bond because that would put 10 electrons around oxygen. We can only fit 8. So second row atoms aren't expanding their octets, so we keep with 8 electrons around oxygen. And then we can have resonance, so we can resonate that double bond over to here, this double bond back over to here. So we can imagine resonance, but the resonance effect isn't super important because what's really important in chapter 9 is counting domains. So it's counting 1, 2, 3 total domains. 3 domains kicks it into trigonal planar. I don't even think I have to sketch this as being close to 120 degrees. Like I don't have to resketch it. I could. Like I could try to resketch a trigonal planar structure, but I can also say, well, I know there's a lone pair, 2 domains, it's going to be closer to 120. Lone pair repulsions, even a little less than 120. So it doesn't take that much time to resketch, but it just means like I could resketch this and kind of show that this should be closer to 120, and lone pair repulsions, a little less than 120. And so this would be bent. So anytime we have 3 atoms, it's either linear or bent. This case here, definitely not linear, so this would be bent. So for OF2, sort of same thing of 3 atoms, so they're all connected together, and is it going to be linear or is it going to be bent? And to get that, we would just count 6 plus 14 for 20 electrons. So that's O, F, F. And I'm kind of already, thinking that it has some lone pairs on oxygen, so it's going to be bent. I kind of already know that. Because when I do 16 electrons here, the 4 left over electrons go on oxygen. So this is going to look a lot like water. And so this is going to have a tetrahedral electron domain geometry, and then the molecular geometry is going to be bent. So close to 109.5 degrees, but probably a little less than 109.5. Again, because of the greater lone pair bond pair repulsions. Oh yeah, we haven't gone through polarity. Yeah, good question. Good. No, or like I totally forgot to go through polarity, so thanks for bringing that up. And so yeah, so we have a difference of electronegativity. And so we get a partial negative charge on nitrogen, not balanced by hydrogen, so we would definitely have a polar molecule for HCN. Ozone is actually a peculiar molecule because we have a positive charge here, negative charge on the oxygens, and so we actually do have a polar molecule for ozone. Now why? I think this is a little bit peculiar is because you may say, well, the oxygens are the same atom. How can one oxygen have a greater pull for electrons than the other? It's not so much that we're saying that that's the case. What we're saying is if you just look at the Lewis structure, you get a positive charge on O, you get a negative charge on the other O, so you get a difference in charge between the oxygens. So we'd have a polar molecule for ozone, and that's despite being just oxygen atoms. And so the polarity comes from the charge difference. So it comes from having positive charge on this side of the molecule, negative charge on this side of the molecule. Having that charge imbalance makes the molecule polar. I think the dipole moment of ozone is like 0.12 dBi or something relatively small. So it's not very polar, but it does have a difference in charge that you can pick up from its Lewis structure. And then OF2, fluorine's more electronegative, pulling electrons downward, positive charge on oxygen. So it's kind of like water, but where now the central atom is positively charged and then the outer fluorine's negatively charged. So definitely polar for OF2. One thing that if you're ever doing like a Lewis structure and you're trying to predict polar versus nonpolar, a lot of times you can just Google polarity, or like what's the dipole moment of the molecule name, and it usually will just pop right up in Google. It's usually right on the Wikipedia page for the molecule. So if you're ever like predicting something should be polar or nonpolar, you can probably look up and see if it has a zero dipole moment, if it's perfectly nonpolar, or if it has some non-zero dipole moment. Yeah. Well, can you use formal charge to predict polarity? So what I would say is, if you can look at like ozone, where the formal charges are non-zero, then you can tell from the formal charges not being zero all the way around that helps you see that it's polar. Whenever you then look at like OF2, the actual formal charges are all zero, then you have to think about electronegativity differences. And so once you think about electronegativity differences, that's how you kick oxygen and OF2 to being positive, the fluorines into negative. So formal charges are kind of a good, like before you consider the relative differences of electronegativity of the atoms, what are the formal charges? And if they're zero, then you say, okay, are some of the bonds polar or nonpolar, and changing that prediction. For like, if we go back to ozone, you get plus and minus before we think about differences of electronegativity. Well, there is no difference in electronegativity. So if we have formal plus and minus already, then those charges should kind of maintain. Because there's no imbalance of, like, there's no way that the atoms, because they don't different charge, are going to reverse those formal charges. Does that make sense? Okay. So thinking formal charges, it's best if our Lewis structure is sort of what the charges are before we take into account electronegativity, where electronegativity is going to make the more electronegative atoms more negative, and then the less electronegative atoms more positive. Okay, so let's go back to looking at things like octahedral and trigonal pyramidal and start thinking about what happens when we replace one of the bonding domains with a pair of electrons. And so one of the things that happens with trigonal planar, this hasn't come up for, this doesn't happen with trigonal planar or tetrahedral. What happens with octahedral is we could imagine replacing one or two different spots with a lone pair. So a molecule that does this is SF4. So SF4 would have 6 plus 28 for 34 electrons. So SF4 is going to have sulfur, 4 fluorines, and then lone pairs on all the Fs. So that's 32. So we have not 0, we have 2 electrons left over to go onto sulfur. So there's 2 electrons onto sulfur, and then what kick SF4 into being 5 total domains. So 5 domains fits the trigonal bipyramidal. And then which of the spots do we want the electron pair to go into? And this is a tricky question, and the answer is actually going to come from nature. So I think we can predict or just understand that we can put the 2 electrons here, and that gives us one geometry, or we could put the 2 electrons here, and that gives us a different geometry. And it ends up being here. So this is the one that wins. So we put the electrons on the equator of the molecule, and then if you could pick up your paper and kind of teeter-totter it, the name is actually seesaw. So SF4 takes a weird geometry name of seesaw, so we call this the seesaw molecular geometry, because it kind of looks like a teeter-totter or a seesaw. I think that's on a separate slide. Let me real quick. Yeah, so that's on this slide here. So for trigonal bipyramidal, where we have 4 bonding domains, but 1 non-bonding domain, so we have to replace one of the domains with a pair of electrons that we choose an equator position. And the reason why, you may wonder, well, why is this? Well, one of the reasons why is that if you just go to SF4 and look at its structure, it looks like this. And so nature kind of defines that this must be the structure that has the lowest overall repulsions of that lone pair with the bonding pair electrons. And so this is the shape emerged for something like SF4. ClF3 is one where chlorine has 2 pairs of electrons, 3 bonds to fluorine. And so this molecule here then is going to put a second electron pair also on the equator position. And so we put 2 electrons on that sort of equator, the equatorial position of our trigonal planar. And then notice that if you take this structure and then rotate your paper, that it looks like a T. And so we call this structure the T-shaped molecular geometry. So if you just look at the atoms, it's like, what are we naming this shape here? And it's like, well, it kind of looks like a T. What are we naming this shape here? Well, it kind of looks like a teeter-totter or a seesaw, so we call it the seesaw geometry. So if you can picture the structure, you can probably choose the right name that fits the atom geometry. And just remember that the geometry name is just the geometry of the atoms. The lone pair matters because it's what gives it that geometry, but we just don't name the electron pair along with the atoms in the geometry name. So we would call this the molecular geometry name. The electron domain is still trigonal bipyramidal. So all the domains still fit into being that trigonal bipyramidal shape. And then xenon F2 now has xenon with 3 pairs of electrons. If you do the Lewis structure, you see it has 6 electrons left over, goes on to xenon. So we have 2 bonds, and then we have 3 non-bonding domains for a total still of 5 domains, and then they just cap off the equator. So for trigonal bipyramidal, if we have electron pairs, 1, 2, or 3 electron pairs with the difference being bonding pair domains, that we're putting those on the equator relative to each other. So we're just putting 1 versus 2 versus 3 electrons on the equator. Let's think a little bit about polarity that we would expect for these molecules. If we had PCl5, so if we have chlorines here, I think we can agree pretty easily that if those chlorines are on the outside of the molecule, we have the same negative charge on all the ends of the molecule. The 2 opposite cancel, the 3 that are trigonal planar cancel, we end up with a perfectly nonpolar molecule. So I think that's pretty easy to see, that same negative charge all the way around. And if you have linear, trigonal planar, tetrahedral, trigonal bipyramidal with the same atom in every spot, it's going to be nonpolar every time. And then if you go to xenon F2, where you have the 2 fluorines opposite each other, this is just like CO2, where those dipoles are canceling each other out. So those dipoles cancel, we also end up with a perfectly nonpolar molecule. But then SF4, ClF3, they don't cancel out. So they are not exactly opposed with atoms. You have to think atoms oppose, it's their nuclei that pick up the net negative charge. You might think the electrons have a negative charge. Don't let that confuse you. It's the net charge on the nucleus of the atom that's pulling electrons towards itself. And so we have a net difference of charge here because we have a net negative atom here, and then net negative atoms here, mostly canceling, but a net negative pull this direction on the molecule, and a net positive charge in that center. And so what we're going to have for ClF3, we're going to have a polar molecule, the same thing with SF4. So we have polar molecules here because they're not opposed. They're like missing the atoms on the opposite side of the molecule to balance out their charge. And so we end up with net dipole moments for SF4 and ClF3. We can also look at the T-shaped molecule and imagine that perfect 90 degree angle is going to be a little bit perturbed. So if you're looking at ClF3, we can even come back to the lone pair repulsions, pushing those bond angles to be a little less than 90 degrees. So we can even predict some structural changes due to those lone pair bond pair repulsions. I think that also helps us picture net charge building up this way, positive charge on that opposite end of the molecule. And so then kind of capping off octahedral, so if we go through octahedral, we can have all the domains be bonds, so that's something like SF6 that we saw earlier, being octahedral molecular geometry. Octahedral though is actually simpler when we replace any one of the positions with a lone pair. It doesn't matter which one we choose. We can choose the down position, we can choose here for electron pairs, we can pick any position, they're all the same, because all the atoms are on an axis together. So we don't really have equatorial versus axial positions. So if you notice, all these atoms are on an axis together, so you can replace any position with an electron pair. And notice if you do so, what shape might you call this if you don't look at the name? You might think, well, I get a square and then just one pyramid. So it's square pyramidal. Kind of like trigonal pyramidal, we get square pyramidal. So we get a square pyramid shape. BRF5, do you think BRF5 would be polar or non-polar? What do you guys think? We get a net pull up towards that top fluorine, not balanced by the bottom, so we definitely have a polar molecule. SF6 kind of continues the trend. If you have the same atom in every spot of a base geometry, like, again, linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral, that molecule would have to be nonpolar. And then lastly, if you have 2 electron pairs, I don't think we want to have 2 electron pairs 90 degrees, right? We would want the electron pairs to be 180 relative to each other. And so the best geometry for 2 non-bonding domains, 4 bonding domains is square planar. Now square planar has 2 atoms that are still on an axis together. And so this molecule here would be perfectly nonpolar. because those bonds opposing each other cancel out their dipole moments perfectly. Okay, so we can predict polarity trends, so we can just sort of picture, do we get some change in structure? We want something that's kind of like bent or has a electron pairs opposite another side of the molecule for a molecule to be polar. If we had the same atom on every side of the molecule, either with no lone pairs or something like square planar, perfectly nonpolar. All right, guys, so that's kind of going through all the base geometries and their structure. Where we go on from here is just a little bit of review next time of this, and then we'll get into some different bonding models for these types of molecules and what their electrons are doing. All right, guys, that'll do it for today. Have a great weekend. See you on Monday.
Oh my gosh. I lost my voice, sorry. But I had a question. So